Hi, welcome back. Today we're going to continue our discussion on day 3 with partial derivatives. And we're also going to be talking about implicit differentiation and related rates, something that might bring back a little bit of memories from last year in Calculus 1 and 2. So we talked earlier in another video, if I'm trying to find the slopes in the x or y direction, we look at the partials in that direction. For example, if I want to find the slope of a tangent in the direction of x, at some point we would calculate the following: the partial with respect to x. If I want to find the slope in the direction of y, we would take the partial of the partial derivative function with respect to y. So we can take a look at an example. Here we have a function f of x, y, and we are looking for find the slope of the tangent in the direction of x and the direction of y at the point 1, 1, e. So if I want to find in the x direction, I will take, my rule says, I take the partial with respect to x. So it would be the partial with respect to x. And remember, we're going to treat y like a constant. So this just becomes e to the xy times, don't forget chain rule. There is a chain rule up here. So the derivative of xy, well, if y is my constant, then this just becomes y, because the power goes to 1. And I could just plug in my point, the slope in the direction of x at 1, 1, e, which just becomes, what would that become? E to the 1 times 1 times 1, or just e. And I can do the same thing for the y direction. I guess I didn't have to put the e there, it should just be the 1, 1. Mainly because we're only looking at the z component, their x and y components. Alright, so the partial with respect to y, same thing as before. This is going to be e to the xy, but this time we're multiplying it by x. Because x is my constant, the derivative of xy is just x, because my variable is y in this case. And if I want to find the partial in the exact slope in 1, 1. Now remember, this is x and y. We only have x and y's here. That's why I didn't need the e before. And of course, this just becomes e as well. Very easy to do. So how can we use partials to find rates of change? Well, let's take a look. So given a parallelogram with adjacent sides a and b. So I'm going to draw a parallelogram with adjacent sides a and b. Okay, there's a. And there's B, and an included angle theta. So we'll put theta there in the middle. We want to find the rate of change of the area with respect to B, given that A is 4 and B is 3. So they're telling me A is 4 and B is 3. And they want me to find the rate of change of area with respect to B. So if I think of my area formula, and I'm going to use my trig formula from pre-calc, the area for a parallelogram is A times B times the sine of theta. We are only looking to find the rate of change, and the only variables we want are area and B. In other words, for us, little a and theta are constants. So everything else is a variable. So what I'm looking to find here is the partial of A with respect to B. So the only ones I want are A and B. So when I take my derivative, if I take the derivative of this with only area and B as my variables, I treat A and sine of theta like they're constants. So when I take the derivative, what we're going to wind up with is just, remember, B is my constant. My power rule says to bring down the 1 and the B goes away. I'm just left with A sine of theta. And at the point at where A is 4, B is 3, and theta is 30 degrees, I can get the rate of change of area with respect to B as the following. I can just plug it in. 4 times the sine of 30 degrees, and that's just 4 times 1/2, or 2. So what this is telling me, all this tells me is, how does the effect how does only changing B affect the area? In other words, we're not worried about changing the angle. We're not worried about changing the side A. We're only worried about changing side B. How does only changing this length right here affect our area? And of course, we can have a little bit more fun. Using the information above, find the rate of change of the included angle. So now we're only looking at theta with respect to side A. So now, only A and theta are the variables. A and theta are the variables, which means A and little b are constants. And that does make it a little bit tougher for us. What we're looking for is to find the change in the angle. How does the change in the angle over the change in area? Now remember, what this is asking us is how does the change in the side affect our angle, in this case right here. And this is implicit. Now, there are a few ways we can do this, but multivariable does make this a little bit easier. We worked with implicits last year, but watch what we can do with this. How multivariable functions help us. Well, we know that the area is A, B, sine theta. Now, if you notice, we're looking at the change in theta and how it's affected by the area. So what we wind up with here is a product rule, because those are two variables. So we have a product rule. These are my two variables, A and theta. So when I take the derivative, well, A is a constant. Its derivative is just going to become 0. Equals, taking a derivative over here, if I treat A and B and sine of theta as my two functions, the first, AB, times the derivative of theta, which becomes the cosine of theta. But remember, there's a chain rule right here. We're taking the derivative of theta with respect to A, so I get the partial of theta with respect to A. Plus the second, which is the sine of theta, times the derivative of the first. Now, A is my constant, so the derivative of my first is just going to be B. Now, there is a chain rule, but it's going to be the partial of A with respect to A. Remember, we talked about that last year when we use implicit derivatives. It's just the partial of A with respect to A, which is just 1, so we never write that. So there is our derivative. And if I solve for the partial of theta, my derivative, with respect to A, we're going to get negative sine theta B divided by AB cosine theta. And if you simplify that, what is that going to become? Look, the B should cancel out. Sine over cosine is tangent, so we should get negative tangent of theta over A. And then you can solve for your answer right there. Now, there is a shortcut for this, and we're going to talk about this later on this unit. There is a shortcut. The partial of theta with respect to A is a negative partial of A with respect to theta. But we're going to talk about this later on this year, and some of you might have looked it up already. So there is a shortcut for this for implicit differentiation. We'll talk about that later on. And then, of course, you can just plug in your angle and, of course, plug in your A. All right. If you go to part 2, we'll take a look at a few more examples. I'll see you then.